Now, after considering resistor, we shall consider one more important component that will be used in most of the electronic circuit is capacitor. The capacitor, represented by the symbol C, we're going to have C1, C2, C3 or CA, CB, or it can be any suffix. It is now represented by a symbol, one horizontal line and one curved line separated by some distance, or it can be represented by two parallel lines of same length. The unit of capacitance is farad, will be represented as F. The capacitance value varies from farad, microfarad, nanofarad, picofarad and femtofarad. So this micro is 10 power minus 6, nano is 10 power minus 9, pico is 10 power minus 12 and femto is 10 power minus 15. Usually the capacitance values will not be specified in the form of kilofarad. It will not be specified in terms of megafarads. Now these are not valid representation, or a typical values of the capacitor will not be in terms of kilofarad or megafarads. So we'll be coming across the capacitance values in the form of microfarad, nanofarad, picofarad or femtofarad. So as we discussed in the resistance, we will going to have the resistance was concentrated at a particular point. We called it as lumped resistor. So we called it as lumped resistor. Even in case of capacitor, we will going to have the capacitor in the form of lumped capacitor. So this is lumped capacitor, or it can be a parasitic capacitor. So this is parasitic capacitor. If it is lumped, usually for any dimension or any value of the capacitance, the lumped capacitor size remains almost the same. And even this in lumped capacitor, we're going to have different category of capacitors, like ceramic capacitor. We're going to have ceramic capacitor. We're going to have electrolytic capacitor. So these ceramic and electrolytic capacitor size almost remains the same across the range of capacitance value. Now that is regarding the lumped capacitors. We will see the examples of this physically, see okay, how does a ceramic capacitor will look like, how does a electrolytic capacitor will look like. So how does this parasitic capacitor, from where it comes? So as the name itself indicates, it's parasitic capacitor. It is due to the presence of charge carriers in a semiconductor devices. So we know that capacitor will be formed because of two parallel plates having separated by a dielectric medium. So this is dielectric medium. So on one side you're going to have positive charges, on the other side you're going to have equal amount of negative charges. So this is how a capacitor behaves. So we're going to write C is equal to epsilon A by D, where A is the area of the capacitance, D is the separation. Now as we see here, so this is how a physical capacitor will look like. So you're going to have a dielectric medium in between two parallel plates, and on one side will be plus charge and the other side is the negative charges. Now is it possible to have these charges of one positive side, one side, negative side, other side, separated by a dielectric medium? So it is still possible in a PN junction. Suppose if you consider a PN junction, so PN junction, we're going to have P-type semiconductor on one side and the N-type semiconductor on the other side. So whenever we join P-type and N-type, we know that, so there is a barrier formed. So there is a barrier formed. So this barrier eventually prevents the moving charges crossing this junction. So this barrier is nothing but acts like a dielectric medium. So this is like a dielectric medium which opposes the flow of electrons from n type to p type and p type to n type, the holes from p type to n type. So this results in formation of charges on the p and the n side. The p and the n side, we're going to have these charges which are being formed. We can just certainly relate this p-n junction having a barrier between the p and n semiconductor material is exactly replacing the dielectric medium. The charges, that is plus on one side of the plate, negative on the other side of the plate, is exactly resembled by the ions on one side of the barrier and the negative and positive ions on either side of the potential barrier. So this exactly represents a capacitor action. The capacitor action, meaning there is a capacitor existing in a p-n junction. So this is not intentionally made out. Because of its structure and the properties of p-n junction, we have a capacitance being get formed. So this type of capacitance is known as parasitic capacitance. So whenever we have any electronic devices with a p and n junction, so there is a capacitance by default being represented in the form of a parasitic capacitance. So the representations again the same capacitance, so it will be represented by capacitor. So depending on what is the terminal, we write it as that particular. Suppose if we consider a transistor which is made out of two junctions. Suppose if I write a NPN transistor, so I'm going to have, so if I say this is my NPN transistor, this is NPN transistor, let us identify the terminals as collector, base and emitter. So as we learned in the PN junction, so there is a barrier formed. So for every PN junction there is a barrier formed. I have a P here, I have a N, so there is a junction formed. So there is a junction formed here. So there is a P, there is a N here, so there is a junction formed, meaning that there is a capacitance existing between this and this. So we write it as C of CB. So this is capacitance between collector and the base. So I'm going to have a capacitance between collector, sorry, the emitter, it is capacitance CB. So there is a capacitance between base and the emitter, there is a capacitance between collector and the base. So these are called as parasitic capacitance. Here we are not connecting any lumped capacitor as we discussed in the previous case. So in the previous case of resistors, you might have seen that the resistance value or the size of the resistor is independent of the value of the resistance. But here in case of capacitors, if the dimension of this device changes, then this capacitance will change. So as we know that epsilon is equal to C A by D. So this D happens to be the thickness of your junction barrier thickness. A is the dimension of your device. Epsilon is the dielectric constant. So we're going to have, this is a parasitic capacitance, which is again now represented by, we call it as junction capacitance. So this is junction capacitance. So there is a parasitic capacitance due to the junction, due to PN junction. So this is called as junction capacitance. So this is in case of bipolar junction transistor. So it is bipolar means because there are two PN junctions possible. So similarly, we're going to have, we'll see one more electronic device which is prominently used in present circuitry, that is MOSFETs. So in MOSFET also we're going to have these parasitic capacitors. So MOSFET, you'll be learning in later classes what is this MOSFET is. So it consists of source, drain, it will going to have a gate structure. So it will going to have a gate structure. So this is the gate, which is made out of metal here. So this is the oxide, which is a dielectric material. So this is dielectric material, and this is again a semiconductor. This is a semiconductor. So you can see there is a semiconductor here, there is an oxide layer which is a dielectric, there is a conductor. So we have conductors separated by oxide. So there is a capacitance between this gate and this semiconductor, which we usually call it as bulk. So we write that capacitance between gate and the bulk as CGB. So this is the capacitance between gate and the bulk. This is a oxide capacitance. So this is a oxide capacitance. Why it is called as oxide capacitance? Because it is due to the presence of the dielectric material, which is in the form of oxide. So that's why it is called as oxide capacitance between gate and the bulk. See here, this is a semiconductor which is of a particular type. If it is of p-type semiconductor, usually this will be the source and the drain will be of n-type. So if this is p, that is n and n. If this is n, they'll be different. So if you have this as n, so then this will be p. So this is also p, meaning that whatever the bulk is, you're going to have the opposite of that in source and drain. So does it mean that you will have a P and N junction, here, which will form a capacitance like CDB and CSB? So what is the CDB? It is between drain and the bulk, between source and the bulk. So these two are junction capacitance. Why it is junction capacitance? It is purely because it is a capacitance due to the presence of PN junction. Here you have a P, you have a N. If this is N, you will have a P there. So this is PN junction. So whether the bulk is N type or P type, will always end up with a junction capacitance between the drain and the bulk, source and the bulk. So whether it is a lumped capacitor, which is purely concentrated at a particular point, will have some capacitance. It can be parasitic also, which is due to the presence of devices like diode. We're going to have the BJT and the MOSFET, or the general electronic devices, which will be dealing. All the three will going to have a capacitance. So this will going to have a junction capacitance. This will also going to have junction capacitance. This will also have a junction capacitance plus the oxide capacitance. So this way the capacitance is slightly different in its existence. It can be in the form of lumped or parasitic. The parasitic is due to these three possible devices, which we'll be repeatedly using in electronic circuits. Coming to its dependency. So earlier we found that the resistance, while discussing the resistor, we concluded that the R value is independent of the frequency, the R value is independent of the amplitude, as long as it is operating in the safe region. When it comes to capacitor, then what is the what is the opposition by this capacitance? Will it allow all the signal? We define something what is called as reactance. We will not say resistance, we call it as reactance of capacitor. Reactance of capacitor, which is called as, which is represented by x suffix c, is given by 2 pi f into c. This is the reactance of the capacitance, which is analogous to resistance of a resistor, but it is not said as resistance of a capacitor. It is a special word, reactance of a capacitor, which is given by 1 over 2 pi f into c. This f indicate the frequency of the signal which is across the capacitor, and c is the value of the capacitance. So as we can see, the reactance is a function of frequency. So naturally, as the frequency of the signal is more and more, the reactance of the capacitance is less and less. So if you consider a DC signal, where the frequency is 0, meaning because DC signal is one which is constant. So this is a DC signal, 1 volt DC signal. What is the frequency of that? 0. Then what is the reactance offered by that? So as we saw in the previous case, as f increases, xc reduces. Similarly, as f reduces, xc increases. So this is the other way. So here we are seeing f is reducing, x is increasing. So what is the least possible value of frequency? It is 0. Then xc will be the maximum. So xc is equal to infinite, meaning a capacitor will offer infinite resistance for a DC signal, meaning a capacitor, if it is connected to a DC source, it will look like a open circuit. Why it is open circuit? Because its impedance is infinite. Of course, we say it is a reactance, its unit is still ohms. The reactance of capacitance is again represented in the form of ohms.